suggests, today what I'd like to do is talk about some new problems in the theory of linear algebraic groups involving reduction considerations. So more precisely, I'll first review exactly what we mean by good reduction for algebraic groups. Then I formulate a certain fineness conjecture and indicate some of its applications. But before getting into linear algebraic groups, just to give a little bit of historical and philosophical context for these kinds of problems, I'd first very briefly like to discuss the use of reduction techniques in number theory and arithmetic geometry, where such ideas first arose. Okay, so first of all, it's been known for a very long time that reduction techniques can be used to show that certain equations have no integral or rational solutions. So for instance, let's take the equation x squared minus 7y squared equals -1. And suppose we want to show that it doesn't have any solutions. Well, if it did have a solution, then we could reduce the resulting equation mod 7, and we arrive at the congruence that -7 minus 1 is a square mod 7, which of course is not possible. So therefore, we have no integral solution. So these kinds of techniques have been around for a very long time. But the point is that in the 20th century, it was realized that beyond detecting the absence and sometimes also the presence of solutions, reduction techniques can also be used to understand the structure of the solution set, or in other words, the set of rational points of their corresponding algebraic variety. And one of the most, well, historically, one of the first and certainly one of the most telling examples of this occurred in the arithmetic theory of elliptic curves, specifically in the Moore-Delvey theorem. So recall that according to this result, if we have an elliptic curve E over a number field K, then the group of K rational points of E is a finitely generated abelian. And the initial case of this theorem was handled by Moore-Delvey in 1922, so for elliptic curves over the rational numbers. And an important step in his argument, which is now often referred to as the weak Moore-Delvey theorem, was showing that the quotient E of Q mod 2 of Q is fine. And here, I mean, although Moore-Delvey didn't really phrase things in this way, ultimately the argument relied on reduction considerations. So since this section is really just largely motivation, I won't go into the details, but I would like to say what we mean by reduction in this context, and also then indicate one key step in the argument. Okay? Okay, so suppose we have our elliptic curve over Q. Well, then since we're working over a field of characteristic 0, we can assume that our elliptic curve is described by the affine equation y squared equals f of x, where f is the cubic polynomial that I have on the slide. And the point is that it has no multiple roots. And furthermore, we'll assume, as we may, that a and b are actually integers, and we take a prime p greater than 3. Well, then we can reduce this equation modulo p. And then one of two things can happen. So the first is that our reduced polynomial still has no multiple roots. And then the reduced equation defines an elliptic curve, but now over the finite field of fp. And we say that our curve has good reduction at p. The other possibility is that our polynomial does acquire multiple roots, in which case we have a singular curve and we say that our original equation has bad reduction. And of course, it's easy to see from this definition that the primes of bad reduction are precisely those that divide the discriminant of our cubic polynomial. So in particular, this is just a finite set of primes. And now, given an elliptic curve P over Q, we'll say that it has good reduction at P if it admits an equation as we had on the previous slide, which has good reduction at P, and otherwise we say that it has bad reduction. Now, this definition is certainly very down to earth and is more than sufficient for our purposes, but let me just mention that, using the language of arithmetic geometry, one can give a much more natural definition, basically saying that our elliptic curve has a model over the valuation ring at P. And we won't need this definition right now, but when we get into linear algebraic groups a little later, the scheme theoretic point of view will become much more important. Now, one thing that I should say is that one has to be a little careful when working with this definition of good reduction. So for instance, if we take the elliptic curve given by the affine equation y squared equals x cubed minus 625x, then this equation certainly has bad reduction at 5. But the elliptic curve can also be described by the equation y squared equals x cubed minus x, which has good reduction at p. So the point is that when working with this definition of good reduction, it may not be sufficient to look at just a single affine equation to determine whether or not our curve has good reduction. In any case, let me now return to the Weak-Mordell theorem. So remember, we're working with an elliptic curve E over Q. And so let's take S to be the set of primes of bad reduction together with 2 and 3. And then for a point defined over the algebraic closure, we denote by Q of R the residue field of R. Okay, so for the proof, one considers the doubling isogeny on our elliptic curve that takes a point P and multiplies it by 2. And really the key point that's very much at the heart of the argument is to show that if we take a prime P outside of our bad set S, then for any Q rational point P and any point R lying in the preimage of P under the isogeny pi, the resulting field extension is unramified at P. And once we have that, one can use some fairly standard considerations from number theory, such as the Minkowski theorem and Kummer theory, to conclude the argument. In particular, in the special case that the 2 torsion of our elliptic curve is defined over Q, this argument ultimately gives an upper bound on the size of the desired quotient that depends really just on the size of the set of primes S. Okay, so this, this is a rough sketch of the proof of the Weak-Mordell theorem, and this argument certainly shows the utility of looking at primes of good and bad reduction. But one can go a little further and ask if, considering this set of primes, one can deduce some more intrinsic information about the curve E itself. And in this spirit, Schaferevich observed in his 1962 ICM talk that if S is a finite set of primes, then there are only finitely many isomorphism classes of elliptic curves E over Q, which have good reduction at all primes P outside of S. So in other words, what this result says that an elliptic curve is determined at least up to finitely many possibilities by its primes of good reduction. And although Schaferevich's argument was very specific to elliptic curves, he nevertheless felt that his result was a particular case of a much more general phenomenon. And this motivated him to formulate the following conjecture. So what he conjectured was that if K is a number field and S is a finite set of primes of K, then for every integer G, there exists only finitely many isomorphism classes of abelian varieties of that dimension, which have good reduction at all primes P outside of S. Now, this conjecture proved to be extremely influential and set off a tremendous amount of activity in arithmetic geometry. And ultimately, the conjecture was settled by Faltings in 1982 as a culmination of a long line of work in this direction. And as is well known, besides being of considerable interest in its own right, this conjecture has a number of other consequences, such as Mordell's conjecture on the number of points of curves of genus greater than or equal to 2, as well as Schaferevich's conjecture for curves with good reduction, again, of genus greater than or equal to 2. And of course, these reduction considerations remain central to many problems in arithmetic geometry up to this day. Now, today, what I'd like to do is to, well, very broadly speaking, talk about work which strives to address some analogous considerations in the context of linear algebraic groups. Okay, so having given this short historical and philosophical motivation, I would now like to transition to talking about linear algebraic groups. Okay. Now, before diving into the formal definition of good reduction for algebraic groups, I would first like to consider several concrete examples that already illustrate some important points when dealing with reductions of algebraic groups. And I should say that although the examples that I will consider involve algebraic groups over Q, just for the sake of being as concrete as possible, in fact, the general definition that I'll give in the next subsection works over any field equipped with a discrete valuation. So the restriction to Q is really not such a big deal. Okay, so let's first look at the group SLN. Well, so first let's think about this a little informally. So this algebraic group is defined by the condition that the determinant is equal to 1. So of course, that's a polynomial condition with integer coefficients, which we can then reduce modulo p. And then we get a similar condition over the finite field fp. So this suggests that the reduction of SLN mod p is again SLN, but over the finite field fp. Now, the way we can make this argument a little more precise is to say that, well, we can view G as a group scheme defined over Z, represented by this quotient of the polynomial algebra that I have on the slide. And then we can consider the reduction of this algebra modulo P, and we get an algebra of a similar form, but now over the finite field Fp. And clearly this algebra represents the group SLN over Fp. And so therefore, as we kind of intuitively know, the reduction of SLN mod P is SLN over Fp. Now the story is completely analogous with split tori. So if we take a d-dimensional split torus, then it's represented by this ring of Laurent polynomials over Z. We can reduce this ring mod P, and we get a similar ring over Fp. So this means that the reduction of the split torus mod P is again a split torus over Fp. Now the common feature that I'd like to emphasize in these two examples is that in both cases, our groups have a nice integral structure, which we can then reduce modulo P to obtain an algebraic group of the same type over the finite field Fp. Okay, so these are kind of the good cases. The next two examples, however, illustrate examples of a different nature. Okay, so specifically for this next example, let's fix a prime P greater than 2 and consider the quadratic extension Q join square root of P. Well, as is well known, we have a norm map from L down to Q. And then there exists an algebraic group G over Q, which is usually referred to as a norm torus, whose group of Q rational points consists precisely of those elements of norm 1. Now, we can give an explicit matrix realization of this group by considering the regular representation of the field extension L over Q. And so I've written down the matrices that make up this group explicitly on the slide. And the point is that, using this matrix realization or other considerations, one can show easily that this group is structurally a one-dimensional anisotropic form. Okay, so now we have this matrix realization. And from that, we see that our group is described by these three polynomial equations on the entries of our matrices. Well, the point is that this is a system of polynomial equations with integral coefficients, which we can then reduce modulo P. And then what we see is that we arrive at a system of equations whose set of solutions consists of unipotent matrices. So therefore, what happens is that we started out with our torus. We took a system of equations describing this group. We reduced it mod p, and we ended up with a unipotent group. And of course, if we reduce modulo any other prime, then we still get a torus. So in other words, the behavior changes radically after reduction modulo p. Now, this example, of course, involves a commutative algebraic group, but it's easy to do something similar in a non-commutative setting as well. So as before, let's take a prime p greater than 2. But now, instead of looking at the quadratic extension, we instead work with a quaternion algebra corresponding to the pair minus 1p. So recall explicitly what this means is that this is the Q algebra with bases 1i, j, and k, with multiplication described by the standard rules. Now again, we have a norm map from D down to Q, which in this context is usually referred to as a reduced norm. And then we have the corresponding algebraic group, usually denoted SL1D, whose group of Q points consists precisely of the quaternions of reduced norm 1. And the point is that just as in the previous example, one can write down an explicit matrix realization of this group using the regular representation. So I'm not going to do that, but the matrices that we get are quite similar to what we had in the previous example, except somewhat larger. And then one shows that over Q bar, our group is isomorphic to SL2. So in other words, it's what is called a Q form of SL2. So in particular, it's a simple algebraic group. And furthermore, if we take the system of equations that we get from our matrix realization and reduce this system modulo p, we get a group which has a non-trivial unipotent radical. So in particular, it's not reductive. Okay, so again, just as in the previous example, the behavior of our group changes radically when we reduce modulo p. Okay. So just to summarize, so in the first two examples, that is to say SLN and the split tori, we have algebraic groups which have a nice structure over Z, or actually it's even better to view it more generally as living over the valuation ring at P. And the reduction of these structures as a modulo P still give us reductive algebraic groups. On the other hand, in the third and fourth examples, we have algebraic groups where after reduction modulo P, we no longer have reductive groups. Okay, so with these examples in mind, we're led to the following definition of good reduction, which is somewhat similar to the definition we encountered earlier in our discussion of elliptic curves. So we'll say that a reductive algebraic group G defined over Q has good reduction at P if it can be defined by a system of polynomial equations with coefficients in the valuation ring at P, such that when we reduce the system modulo P, we still have a reductive algebraic group. And otherwise, we'll say that our group has bad reduction at P. Okay. Okay, so with this definition, it's clear that the groups SLN and the split tori have good reduction at all primes P. On the other hand, in the third and fourth examples, the situation is somewhat more delicate. So as our computation suggests, the norm torus that we consider does indeed have bad reduction at P and good reduction at all other odd primes Q not equal to P. On the other hand, the group SL1D has bad reduction whenever P is congruent to 3 mod 4. But if P is congruent to 1 mod 4, then our algebra is actually split. So our group is isomorphic to SL2, and hence in particular has good reduction at P. In fact, just to foreshadow something that will come up in just a second, For this last conclusion, it would be enough for us to have the isomorphism not over Q, but just over the completion QP. Okay, so in any case, the thing that I'd like to emphasize is in the good cases, our groups have a nice integral structure, which we can reduce modulo P and still have reductive algebraic groups of the same type after reduction modulo P. And this is the kind of behavior that I'd like to capture in our general definition of good reduction. And this is precisely what we'll be able to do using the language of reductive groups. Okay. So any questions at this point before I go on to the formal definition of good reduction? Okay, so in this next subsection, what I'd first like to do is, well, as promised, give the definition of good reduction in general. Then I'll quickly review the notion of K-forms. And then finally, I'll be able to give a precise formulation of the general problem that we'd like to consider. Okay, so let's take K to be a field equipped with a discrete valuation V. So then, given an algebraic group G, a reductive algebraic group G defined over K, we'll say that it has good reduction at V if there exists a reductive group scheme, script G, over the valuation of the ring of the completion, whose generic fiber is isomorphic to the base change of our group up to the completion. And then automatically the special fiber or the reduction is a reductive algebraic group over the residue field. Okay, so in other words, again, the point to emphasize here is that we're insisting that our group has a nice integral structure, in this case over the valuation ring of the completion. Okay, well, this definition is perhaps somewhat abstract, but it turns out that the condition of having good reduction can be described quite concretely in a number of situations of interest. Okay, well, so first of all, if G is a split group, then it has good reduction at all valuations V. The reason being that by the Chevalley construction, any such group arises from a group scheme over C. Okay. Now, the next example is, well, for any central simple K algebra, we have the group SL1A associated to the elements of reduced norm 1. So this is a generalization of the group SL1D that we saw in one of our previous examples. And it turns out that this group has good reduction at V if our algebra is unramified at V. So in other words, it arises from an Azumaya algebra over the valuation ring of the completion. And one more example that I'd like to mention that will be relevant for us a little later on is that if G is the spinor group of a non-degenerate quadratic form in n variables, then this group has good reduction at V if up to scalars, our quadratic form is equivalent to a quadratic form all of whose coefficients are units in the valuation. Okay, so in other words, this definition of good reduction, which we phrased in terms of reductive group schemes, can be described, in fairly concrete terms in many situations. Okay, so now let me just briefly recall the notion of K-forms.
Sorry,
Yep.
This is not equivalent. I mean, it's not if and only if. Okay, right? The two.
Well, I mean, yeah. So if our group has good reduction, then it's our form is of this type. Yeah.
It must be.
Yeah.
Okay. Thank you.
Yep.
Thank you.
Yep. So right. So let me briefly recall the notion of K-forms, although I probably don't need to do it in this seminar. But just a little bit of context as to why we need this notion. So if you recall, in Schafferevich's conjecture, One deals with abelian varieties of a fixed dimension. Of course, for linear algebraic groups, it doesn't really make much sense to classify groups according to dimension, since we can have radically different groups of the same dimension. So instead, it's far more natural to look at groups which become isomorphic over a separable closure of our field of definition. So namely, if we have a group G defined over K, a group G prime is called a K form of G if the two groups become isomorphic over a separable closure. And just a couple of well-known examples. So if A is a central simple algebra of degree n over K, then over the separable closure, our algebra is simply the matrix algebra. And hence, the group SL1A that we had in the previous example is a K form of SL. And another example, so again, let's return to spinor groups. So if Q is a non-degenerate quadratic form in n variables, and G is the corresponding spinor group, then the spinor group of any other non-degenerate quadratic form Q prime in n variables is a K form of G. And from the classification of such groups, it is known that if n is odd, then these are precisely all the K forms. But for even n, the situation is more complicated, and we may have forms coming from Hermitian forms on division algebras. Okay, so right. So now, having the definition of good reduction and also reviewed the notion of K forms, I can formulate the general problem that we're interested in studying. Okay, so suppose we have a field K equipped with a set V of discrete valuations, and we have a reductive algebraic group defined over K. Then what we would like to understand are the K forms, or even just the inner K forms of G that have good reduction at all V in V. Okay, so of course this is a very general problem, and in order to make this more meaningful and also somewhat tractable, it's really a good idea to specialize the field K, the set of discrete valuations V, and also possibly the group G. So in the next two subsections, what I'd like to do is to describe two choices for the field K and the set V. The first will be what I will refer to as the Dedekind case, where our field is the fraction field of a Dedekind ring. And the second will deal with arbitrary finely generated fields. Okay, so first let me address the Dedekind case. So as I said here, our field is the fraction field of a Dedekind ring R, and the set V consists of the discrete valuations of K associated with the maximal ideals of R. And this situation was studied systematically, first by Harder in the 1960s, and then later by Kaliotinen and Sansuk in the 1970s. And since then, it has received more attention. So the basic case, where R is the ring of integers, was handled by Dick Gross in the 1990s. And then there was also some follow-up work on this topic by Brian Conrad around 2012. Okay, so let me first talk about groups over number fields. So first, an important observation in Gross's paper is that if G is an absolutely almost simply connected algebraic group over Q, then G has good reduction at all primes P, if and only if G is split over all QP. Okay, and using, with this result in mind, Gross was able to construct examples of non-split groups having good reduction in certain situations, and even in some cases completely classify such groups. Now, although this result is no longer true for arbitrary number fields, we do nevertheless have the following finiteness statement, which is derived from some results in the Galois cohomology of algebraic groups of our number fields. together with a description of groups with good reduction over p-adic fields. Namely, if G is an absolutely almost simply connected algebraic group over a number field K, and V is a set of discrete variations, or the set of almost all places of K, then the number of K forms of G that have good reduction at all V and V is finite. Okay, so this is what we can say over number fields. Now, another natural example of Dedekind rings, which is of somewhat more geometric nature, is the ring of polynomials in one variable over a field little k. And here, our corresponding field capital K is the function field in one variable, and V is the set of discrete variations of capital K associated with the monic irreducible polynomials. So geometrically, we're really just working with the affine line over little k, and V is the set of discrete variations associated with the closed point. Now, in the 1980s, Raghunathan and Ramanathan studied torsors over the affine line, and then this problem was revisited by several other people later on. And so one consequence of their results, and I should say that this is not the version of the result that appears in their paper, but it's a consequence for groups with good reduction, is that if K is a field of characteristic 0, and G0 is a connected reductive group over K, then if we take a K form G prime of the base change of our group up to the function field, and we assume that this form has good reduction at all V and V, then it actually arises from a K form of G0 over the base field little k. Okay, so as I said, this is derived from their description of torsors over the affine. So more recently, a similar problem was studied by Chernousov, Gil and Pianzola over the punctured affine line. And although I'm not going to go into the details, from their results, one can derive a cohomological description of the inner forms of a reductive group having good reduction. And so, this result was central to their work in proving the conjugacy of some analogs of Cartan-sum algebras in certain.
So Igor, yeah. This is not totally correct. I mean, this. Are you sure? I mean, that inner forms, because that's the image,
Yeah. So
I mean, this is not important. The image of this thing in the OG0. You see?
Yes. Yes.
So I mean, up to a map, with finite fibers. This is that.
Yeah.
Is
yes.
what I'm saying.
So yeah. Sorry. So yeah, this is not entirely correct, but yeah.
It's almost that. Yes.
Yeah. Yes. Thank you. Okay. Yes. Thank you for that. But now, so we have these examples of groups over the affine line and the punctured affine line, and we can imagine a common generalization that looks something like this. So we can look at a smooth geometrically integral affine curve. Then we can, as our ring, we can take the ring of regular k-defined functions on C, and as our field, a capital K, we take the function field. And then we work with a set of discrete variations associated with the closed points of C. Now, as far as I know, at this level of generality, there is no good explicit description of K forms of good reduction. So we can instead consider the following more qualitative question. So we can ask, when is the number of K isomorphism class of K forms of reductive groups which have good reduction at all V and V? When do we have only finitely many such forms? Okay. Well, before formulating a conjectural answer that is suggested by some of our recent work, I should point out that we really need to impose some assumptions on our field little k for a very simple reason, in order to be able to answer this question. And the reason is that if we have our group defined over little k, and we take a form over the base field and base change it up to the function field, then this is a form which has good reduction at all v in v. So in particular, we need to ensure that there are only finitely many forms over the base field. And so when Serre was studying some finiteness properties of the Galois cohomology of linear algebraic groups, he introduced a certain condition which he referred to as F. So he defined a perfect field to be of type F if, well, roughly speaking, for any integer m, it has only finitely many extensions of degree m. And one can also formulate this group theoretically as I have on the slide. Now, in some recent work, I've considered a certain generalization of this condition. So if we have an integer m, which is relatively prime to the characteristic of our field, then we say that k is of type f prime m, if for every finite separable extension L of k, the quotient L star mod mth powers is finite. And it's easy to show that for perfect fields and any integer m relatively prime to the characteristic, condition f certainly implies f prime m. But the point is that this condition f prime gives us a little more flexibility. So, well, some well-known examples of fields of type f include, the reals, the complex numbers, finite fields, p-adic fields, and so on. On the other hand, this local field of positive characteristic that I have on the slide, that's certainly not of type f, but it is of type f prime m for all m relatively prime to p. And in fact, sort of building on this example, we have a fairly general recipe for producing many, many examples of fields of type f prime m. Namely, if k is a field which is complete with respect to a discrete valuation, and the residue field is of type f prime m, then so is the field k itself. So in particular, we see that if we have a base field of type f prime m, then fields of iterated Laurent series over such a field are also satisfy this condition. Okay, so in any case, this is the kind of condition that I'd like to impose on our base field. And now let's return to our setup. So remember, we had an affine curve. We're working with its function field and the set V of discrete valuations associated with the closed points. Now let's take G to be an absolutely almost simply connected algebraic group over K, and denote by W the order of the Weil group. So then, what our recent results seem to suggest is if the characteristic of our field is relatively prime to the order of the Weil group, and moreover, our field satisfies condition f prime p for all prime divisors of W, then the number of k isomorphism classes of k forms G prime of G, which have good reduction at all v and v, is finite. Okay, so under some assumptions, we expect that we only have finitely many forms with good reduction. Okay, so that's the Dedekind case. Now, the other case that I'd like to look at is when K is a finitely generated field. Now, perhaps one thing that I should point out is that unlike the Dedekind case, this case has not really received attention until quite recently, and our work really represents some of the first steps in this new and interesting direction. Now, what is the setup? Well, K is now a finitely generated field. And then for such a K, we can consider models of the field. So that is to say normal integral affine schemes whose function field is K. And then for any such model, we have the corresponding divisorial set. That is to say the set of discrete valuations of K associated with the prime divisors on X. Okay, so this is a geometric description of the setup, but it's also possible to phrase this in purely algebraic terms. Picking such a model basically amounts to finding a subring R of K, whose fraction field is R, such that R is a finely generated algebra over Z, or FP, and R is integrally closed in K. And then the set V simply corresponds to the height 1 prime ideals of R. Okay. So just to illustrate this setup, let's look at a concrete example. Okay, so let's take the field Q of X, so the field of rational functions in one variable over Q. And for our ring, let's take Z box X. Well, it's well known that for such an R, the height 1 primes are principal and are of two types. So first, we have the primes generated by the irreducible polynomials of content 1. And then we have the prime ideals generated by primes P. And for each type of ideal, we have the corresponding discrete valuations. So those associated with ideals of the first type are sometimes called the geometric places, and those associated with the second type are sometimes called the arithmetic places. And then the divisorial set associated with a model spec R is simply the union of V0 and V1. So this is the kind of setup that we're working in. Okay. So now let me formulate our main finiteness conjecture for groups with good reduction. Okay. So we take K to be a finitely generated field, V a divisorial set of places, and G a reductive group over K. So then, under the assumption that the characteristic of our field is good, in a sense that I'll specify in just a second, we expect that the set of K isomorphism classes of K forms G prime of our group, which have good reduction at all V and V. So this set is finite. Okay, and what do we mean by good characteristic? Well, if G is an absolutely almost simple group, then we say the characteristic is good if it's either 0 or does not divide the order of the Weyl group. And for tori, we consider only characteristic 0 to be good. Okay. So hopefully I'll be able to discuss some results. I should say that, discuss some results later, and I should say that we've been able to verify this conjecture already in a number of cases. In particular, we've resolved it completely for algebraic tori. But before talking about that, I should perhaps say a few words as to why we refer to this as our main conjecture for groups with good reduction. And the reason is that, in addition to being interesting in its own right, and I should, point out that it has some, at least, formal similarities to Shafarevич's conjecture for abelian varieties. So in addition to that, it turns out that this conjecture has close connections to a number of other problems lying at the intersection of the theory of linear algebraic groups and arithmetic geometry. So in the next subsection, I'll indicate one connection to the study of local global principles, or Hasse principles, for linear algebraic groups. Next, when working on this conjecture for spinor groups and certain other kinds of groups, one is naturally led to study some finiteness properties of unramified cohomology. And this conjecture also has important consequences for the analysis of algebraic groups having the same isomorphism classes of maximal tori. So this is sometimes referred to as the genus problem. So hopefully I'll have time to say something about each of these three items. One further connection that I just like to mention but won't address today is that this conjecture comes up quite naturally in the study of certain problems involving weakly commensurable Zariski dense subgroups and applications to some classical questions on locally symmetric space. Okay. So hopefully this provides a little bit of context for for this conjecture, and specifically its connections to various other parts of this theory. Okay. So now, as promised, let me say a few words about local global principles. So first, the general setup in the cohomological approach to local global principles looks something like this. So we have a field K equipped with a set of discrete variations, which, these variations are often discrete but need not be in general. And we have an algebraic group G over K. So then we have the usual global to local map in Galois cohomology. And one says that the local global principle, or the Hasse principle, holds if this map is injective. And furthermore, one defines the corresponding Tate-Schaferage set to be the kernel of this map. Now, the study of local global principles for groups over number fields is really one of the cornerstones of the classical arithmetic theory of algebraic groups. So here, let's take little k to be a number field and V to be the set of all places of K, including the Archimedean places. So then, the key result here is that if G is a simply connected or adjoint algebraic group, then the Hasse principle holds. In other words, the global to local map is injective. On the other hand, it's known that this map may not be injective for arbitrary algebraic groups. But the thing is that it's always proper. That is to say, the pre-image of a finite set is finite. In particular, this means that the Tate-Schaferage set is always finite. Now, what some of our recent work suggests is that this properness should hold in the rather general setting of groups over finitely generated fields. Okay, so here's the precise statement of the conjecture. So suppose that K is a finitely generated field and V is a divisorial set of places. Then we expect that if G is a reductive algebraic group over K, then the corresponding global to local map is proper. In particular, the Tate-Schaferage set is finite. Okay, and a little later, I'll discuss some available results on this. So again, in particular, we've been able to resolve this completely for algebraic tori. But just to finish up this subsection, let me mention the connection to our main conjecture concerning groups with good reduction. And the point is, roughly speaking, is that the conjecture provides a uniform approach to this conjecture too for adjoint groups. And the precise statement looks like this. So suppose we have an absolutely almost simply connected algebraic group G over our finally generated field K. And let's assume that our main conjecture on forms with good reduction holds for G and all divisorial sets of places of K. Then it turns out that the corresponding global to local map is proper for the associated adjoint group G bar and any divisorial set V. Okay, so in other words, assuming the conjecture, for simply connected groups, allows us to resolve this conjecture concerning local global principles for adjoint groups. Okay, and so now in the last few minutes, let me maybe survey, well, not all results, but at least a few. Let me start with a case of algebraic tori, since we've resolved all conjectures there, and then I'll say a few words about absolutely almost simple groups. Okay. So first, concerning the main conjecture for tori, we've shown that if K is a finely generated field of characteristic 0 and V is any divisorial set of places, then for any integer d, the set of K-isomorphism class of d-dimensional K tori, which have good reduction of V and V, is finite. Okay, so let me just mention a few things that go into the proof. Well, first of all, it's well known by general theory that the K-isomorphism classes of d-dimensional K tori are classified by the equivalence classes of continuous d-dimensional integral representations of our absolute Galois group. Then we use a result according to, so it was proved by Faltings in some special cases and by Hiranucci and Harada in general, that for any model of our field, the Tel fundamental group satisfies Serre's condition F. And we use this to deduce that there are only finitely many possibilities for the kernels of such representations. And then finally, to conclude the argument, we use a result which ultimately depends on reduction theory, which is that for any finite group H, there are only finitely many equivalence classes of d-dimensional integral representations of H. Okay, so that resolves the main conjecture for algebraic tori. We've also, and I should say that basically the same argument yields this result for function fields of curves over fields of type F. Now, we've also resolved our conjecture concerning the properness of the global to local map. So we've shown that if K is a finely generated field of arbitrary characteristic and V is a divisorial set of places, then the corresponding Tate-Shafarevich group is finite. And so notice here that since we're working with commutative coefficients, the finiteness of the Tate-Shafarevich group is equivalent to the properness of the global to local. Now, in the classical setting, where our field is a number field, the proof relies on the results of Tate and Nakayama, which of course are not available in general. So instead, we give two proofs. The first one, well, the main ingredient is Gauber's proof of absolute purity, and this requires some minor restrictions on the characteristic of our field. The second one works in arbitrary characteristic, and it basically uses adelic methods in a higher dimensional setting. Now, although I'm not going to go into the details here, I should say that our second proof, and this was somewhat surprising to us at first, it turns out to shed some new light on the classical situation over number fields. So namely, it shows that the finiteness of the Tate-Shafarevich group over number fields can be established without the results of Tate and Nakayama, and instead ultimately follows from two classical statements of number theory, namely the finiteness of the class number and the finite generation of the group of units. So that was a bit of a surprise to us. So that completely resolves our conjectures for algebraic tori. What about absolutely almost simple groups? Well, since I'm pretty much out of time, let me just briefly mention a couple of things. So first, we've resolved the main conjecture for inner forms of type AN over essentially arbitrary finely generated fields. So namely, we've shown that if K is a finely generated field and V is a divisorial set of places, then for any integer n relatively prime to the characteristic, the number of K-isomorphism classes of groups of the form SL1A, where A is a central simple K algebra of degree n, which have good reduction at all V and V. So this set is fine. And then, as I said, we automatically get the properness of the global to local map for the corresponding adjoint group. Okay, so let me not say anything about the proof, which ultimately relies on the unramified Brauer group. And the last thing that I'd like to mention is that although, for arbitrary finely generated fields, we're still working very actively on the conjectures. We've been able to prove quite a number of results over so-called two-dimensional global fields. So these are either function fields of curves over number fields or function fields of surfaces over finite fields. And one result that I'd like to mention concerns the main conjecture for spinor groups over such fields. So namely, we've shown that if n is greater than or equal to 5, then spinor groups of quadratic forms and n variables over such fields. So there are only finitely many isomorphism classes which have good reduction at all v. And we also have similar results for certain other groups, certain special unitary groups, groups of type G2, and we also have some corresponding results concerning local global principles for such groups over two-dimensional global fields. Okay, so I think I'll stop here as far as the material is concerned. Just let me mention some references. So I guess the reference that I'd like to point out is this last paper, item 8. This is a survey paper concerning many of the questions that I've addressed today, and it provides historical context, a precise formulation of the results, and also an overview of some of the techniques that go into the proofs of our results. Okay, so thank you very much. So I think I'll stop here.
Okay, thank you. So, questions or comments? You can use, the chat if necessary.
How close are these questions to showing that there's a finite number of underlying algebraic objects, such as central simple algebras or quadratic forms?
Yeah, so I mean, these questions, I mean, so for example, for the group SL1A, that certainly boils down to studying the unramified Brouwer group, which sort of addresses your question for central simple algebras. For quadratic forms, using results on Milnor conjecture, we're able to reduce these questions to unramified cohomology. That basically boils down to studying fineness properties of quadratic forms. But in general, the issue is that we don't have a good cohomological description of these groups. We don't have sort of good cohomological invariants to work with, so we have to think of something else to do.
Okay, so other question? No? Well, I have one actually, but maybe somebody else before. So my question is about the result on of the Tchefarevich group for tori.
Yeah.
So in the number of Hill case, we have this Voskresensky exact sequence, and this sequence it permits to give some upper bound for the cardinal of this Tchefarevich group. Okay.
Yeah.
And do you have something similar in your setting?
No, unfortunately, our methods are not effective, so they don't give an explicit upper bound. They just show the finiteness.
Okay, and then so in the number fields, we can look also at the chateau,
Yeah.
of the chateau is finite as well. So can you say something also on the chateau and the higher
Yeah,
chat?
actually, so our method actually gives the finiteness of chat of all the higher chats.
Okay, great, good, thank you.
Yep, thank you.
Actually,
So-
do you hear me?
Yeah.
Do you hear me?
Oui. Yes.
Okay, maybe I can start the video. Okay, so I have one comment about this finiteness of SHA for tori over a field finite derivative number field. I think it's not. I mean, okay. My impression is the following: you have your torus T, which is over your field K. So K is the field fraction of some regular ring of finite type of a spec Z. Right?
Yep.
The torus T is good as good reduction over something like this. And then it is split by a finite étale cover of this, provided you shrink a little bit your A. Okay.
Yeah.
And so now, if you take your class in H1 KT, which is you suppose it's trivial in the completions, I think it shouldn't be very difficult to show that in fact the class comes from H1 étale of AT for the model.
Exactly. Yeah.
But then once you're there, you finish basically because you look at the sequence. So you have B over A. So if H1 B over AT goes to H1 AT goes to H1 BT. Now H1 BT is going to be finitely iterated because we know that the Picard group or something like this is finitely iterated by the generalized Mordell theorem and the unit theorem. And the other part is H1 of G with values in T of B, and T of B is finitely iterated. So this is finitely iterated, but then you land in H1 KT, which is killed by some integer.
Yeah.
And so it's finite.
Yeah. So in fact, that's more or less how our proof. So the first proof.
Yeah, and
That's
so
more or
there's
less how it
actually
is.
no, there's no Tate Nakaya or whatever in this story.
Exactly.
It's basically,
Yeah. So
it's basically
not
the key
it's not
ingredients
needed.
are the key ingredients really are the finiteness of the class group for
Exactly. Yeah.
things of finite type, and the unit group is finitely iterated.
Exactly. Yes.
Sorry, the class group is finitely iterated, and the unit group is finitely iterated. So this it piles up Mordell and classical things. Okay.
Exactly. Yeah.
I mean, there's some variation that there are some results like this, but not for this for fields finitely iterated over Q. In the paper with Gilles and Paramala wrote a long time ago, where we're looking at typically fields which are finitely iterated over a finite field or of QP.
Mm-hmm.
Okay.
Thank you.
One last questions, maybe? No. Okay, so if not, we thank Igor again. So, and next week, there will be a talk by Sasha Mercury. Okay. Bye. Thank you again.